Hello and welcome back. In the previous session we derived the magnitude of total compressive force. We could locate the total compressive force. We could also get the lever arm. We could also get the magnitude of total tensile force. Now regardless of the type of the section, which is under reinforced, over reinforced or balanced, which we will subsequently see in much greater depth, for the time being just understand there are three types of section. One is called as the under reinforced section, the other one is called as the over reinforced section, and the third one is called as the balanced section. Regardless of the type of the beam, Cu and Tu, that is total compressive force and total tensile force, will be numerically equal but exactly opposite in the direction. So if I need to know what is my depth of neutral axis, this depth, I can equate the total compressive force and total tensile force regardless of the type of the beam. So I can equate the two. First of all, let's revise what was the total compressive force formula. It was 0.36 FCK XU into B, and the total tensile force was 0.87 FY into AST. Now if I equate the two, I am interested in getting this value of XU. So I'll keep XU on the left hand side and send everybody on the right hand side. So this XU remains here. So we have 0.87 FY into AST divided by this 0.36 FCK into B. So this formula gives us the depth of neutral axis for known values of FCK, Fy, AST and width. So if I know what is my grade of concrete, what is my grade of steel, what is the provided area of reinforcement, and what is the width of the section, I can find the actual depth of neutral axis. So this is a very important calculation, and this formula you must remember. It is simple. Cu is equal to Tu. If you don't even remember, simply remember what is Cu and what is Tu. You can simply equate and form the equation for neutral axis depth. Now if we come back to the strain diagram, the strain in concrete regardless of the grade is given to be 0.0035, but strain in steel depends on what is the grade of steel. So if I have, let's say, mild steel as my grade, the strain would be different. If I have Fe415 as my grade, then the strain would be different. This value, modulus of elasticity for steel, is constant for all the grades. You must have studied the Hooke's law and what is the modulus of elasticity. It is 2 into 10 raised to 5 for steels. So this gives us a very important insight into whether there would be a limiting value of XU up to which the strain would not exceed. Okay, so we always must avoid exceeding the strain, otherwise there would be a failure. So our strains must always be less than this or at the most equal to this. So if you see, there are two triangles that we can form. So we have this triangle, and we have another triangle, which is this triangle. So if I apply properties of similarity of triangles on these two triangles, I am able to locate limiting values for XU, that is the depth of the neutral axis. So if we just go down, strains cannot be allowed to exceed it. So there will be a limiting value of neutral axis depth for each grade of steel. Okay, so strain in concrete is constant 0.0035, but we have mainly 4 grades of steel. One is the mild steel that we all know, Fe250. Then we have HYSD bars, Fe415, Fe500 and Fe550. Now these strain values, if we calculate, we can subsequently calculate some design constants. That is our objective. Okay, so let's focus on one calculation first, and then subsequent is the repetition of everything. So if I go ahead and let's calculate the same for Fe250 steel. Okay, so what does this mean? Fe250, the characteristic strength of Fe250 is 250 Newton per millimeter square. Okay, now we also have written the value of strain here. So again I'll rewrite the same. So strain in steel is 0.87 into Fy upon Es plus 0.002, which is given in clause 38.1. Now I am interested in getting what is the maximum strain or the limiting strain for Fe250 grade of steel. So instead of Fy, I'll have to put 250 and ES, that is the modulus of elasticity, I can substitute the value as 2 into 10 raised to 5. Again, you need to be consistent with units. This is in Newton per millimeter square, so my modulus of elasticity needs to be in Newton per millimeter square again. So I put, and instead of Fy I could put 250, instead of ES I can now put 2 into 10 raised to 5, and that calculation will give me what is the strain in steel for Fe 250 grade. So let's go to the calculator, let's get the calculation done. So it is 0.87 times 250 divided by 2 into 10 raised to 5. So we have 10 raised to 5, and plus this everything is to be added with 0.002. So if we press enter, we'll get the answer, and this is 3. Okay, so this value is 3.0875 into 10 raised to minus 3. Okay, so it is 3.0875 into 10 raised to minus 3. Now this is strain, so it does not have a unit. Okay, you need to remember that. So we got 3.0875 into 10 raised to minus 3. That is limiting value of strain if I am having grade of steel equal to Fe 250. Okay, now let's go to the strain diagram. Okay, and we'll form the similar triangles that we need. So this is one similar triangle that we have. Okay, and then there is another similar triangle that we need. This is the second similar triangle. Now from this, what we can find? We can find the relation. Okay, so XU divided by 0.0035, and this would be, since total is D, out of that we can subtract XU, so this becomes D minus XU, and this height will be divided by this value of strain, which just now we could get for Fe 250 steel. It was 3.0875 into 10 raised to minus 3. Okay, so we have XU divided by 0.0035 and D minus XU divided by 3.0875 into 10 raised to minus 3. So we'll go down and write it in detail that we have property of similarity of triangles, and we can write XU divided by 0.0035. Now if you recall, I have substituted the limiting value because these two strains, okay, if you check this strain and these strains, these are maximum, or in other words, the limiting values of strains, and this is evident from strain diagram just now we saw. So I am interested in getting what is the value for XU limiting. I am interested in this. So what I have to do, I'll have to simplify this equation. So what I can do is I can send this here and send this here. Okay, so XU limiting into 3.0875 into 10 raised to minus 3 is equal to, this is to be multiplied to this entire term. Okay, so this is 0.035, which is this term, into D minus XU limiting. Okay, so if I multiply, this gets multiplied to this as well as this. Okay, so we have 0.0035D as well as minus 0.0035 into XU limiting. Now this XU limiting, this term, the product of this and this is now minus. I can send it to the left hand side. So we have this term, which is 3.0875 into 10 raised to minus 3 XU limiting, plus, because this minus was sent to the left hand side, and this becomes 0.0035 XU limiting. This gives us the product of these two terms, which is 0.0035 times D. Now I am interested in addition of these two. Okay, that will give me some value which I can later on compare with this. Okay, so let's do this calculation. So we have 3.0875 into 10 raised to minus 3. Okay, 10 raised to minus 3 plus we have 0.0035. Okay, so if I do this, I'm getting 6 point, okay, let me erase this first. 6.588 will take 6.588 into 10 raised to minus 3. Okay, let's verify again. This is what we got, 6.588. We are considering 3 significant digits. Okay, now I'm interested in getting this value. I'm interested in getting XU limiting only, right? So what I can do is I can send this value on the right hand side. So again, I'll rewrite this as 6.588 into 10 raised to minus 3. Now this is going to give me the limiting value of XU in terms of the effective depth of the section. Okay, so let's do this calculation again. So we have 0.0035 divided by this term is 6.588 into 10 raised to minus 3. So if you do this, we are getting 0.531. So this is the most important value that you need to remember, that for Fe250 grade of steel, the limiting value of neutral axis is 0.531 times the effective depth. Okay, so there would be two neutral axis depths now. Okay, one is the XU that we could get from calculation of this 0.87 Fy into AST divided by 0.36 into FCK into B. Okay, so if I get this is my actual depth of neutral axis, and regardless of what reinforcement I am putting, what is my grade of steel, what is my grade of concrete, what is my section width, I have a limiting value of XU. Okay, that is the limiting value of depth of neutral axis. It depends only on the effective depth. Okay, remember this. So this is coming from strain limitations. Okay, this is coming from strain requirement. So this value can never be exceeded regardless of what you are having. So whatever is the reinforcement, whatever is the grade of concrete, whatever is the grade of steel, doesn't matter. Okay, in any case, XU limiting cannot be exceeded. So maximum value of XU will always be XU limiting. So this we could get for Fe250. Subsequently, can we get moment of resistance also? Okay, so can we get moment of resistance, which would be the limiting value? Of course we can. So if you recall, we have moment of resistance from compression force. So we had written in the previous session as MR from compression. Okay, since I know now the maximum value of XU or the limiting value of XU comes out to be 0.531 times effective depth. Okay, so I can find what would be the limiting value of moment of resistance or the maximum value of moment of resistance that the singly reinforced beam can resist. So that subsequently will come in detail, but for the time being we are interested in getting the design constants. So let's calculate what would be the moment of resistance for Fe250, that is the limiting moment of resistance. So I'll substitute the formula for Cu. Cu formula is 0.36 FCK into XU limiting, that is the force, and then there is D minus 0.42 XU as our lever arm. So now I'm going to substitute wherever I see XU, I'm going to substitute that with XU limiting. So here instead of XU, I'm putting XU limiting. Here also 0.42 XU was there, so we are substituting XU limiting. I can now do the calculation. So 0.36 into FCK into 0.531D, which is substituted for XU limiting, and here also XU limiting goes 0.531D. Now if you take 0.36 FCK and B outside, then we can do the simplification. So I have taken 0.36 FCK and B here. Okay, and this 0.531D needs to multiply. Okay, so if you can see, this 0.531D needs to multiply to this bracket. So this becomes 0.531D into D, as well as 0.531D into 0.42 into XU limiting, that is nothing but 0.531D. Okay, so now this calculation can be done. Okay, so let's do it here first. Okay, so we have to multiply this. Okay, let's do that. 0.531 into 0.531 into 0.42. So I am solving this portion, 0.531 into 0.42 into 0.531. Now if you see, this becomes d square. Okay, so this comes out to be 0.1184. now this is to be subtracted. Okay, so this, if you can see, this becomes d square, and this into this again becomes d square. That means we can subtract whatever is the answer of this from this. Okay, so this I can subtract from 0.531 minus answer. Okay, so that will give us 0.412. okay, into, now this bracket is simplified into 0.36. so that gives us 0.1485. so that is another very important value that you will have to remember. Now I am considering 3 significant digits, so the simplification of all of this is 0.149 numerically, and then we have FCK, B and square of D. Okay, so this is really important. So for the maximum value of mu for Fe250, the formula is, or the relation is 0.149 FCK BD square. This is really important. Okay, so this value you have to remember. This value comes just by putting or replacing XU with XU limiting in CU and ZU. Okay, so if you replace XU with XU limiting, we get the result as 0.149 FCK BD square. Okay, we have one more design constant which we can calculate, is the percentage of reinforcement. Now percentage of reinforcement is of your cross sectional area, how much is the reinforcement area. So it is having the relation as AST by BD into 100. Now if you come up here, this is the depth of neutral axis relation which we have derived just by equating CU with TU. Okay, now instead of using the same relation, if I can substitute XU as my XU limiting value. Okay, so this is nothing but our XU limiting value, 0.531 T. Now if you check, this is calculated specifically Fy equal to 250 Newton per millimeter square. Okay, this value of 0.531 D is for Fe250. Okay, so I'll substitute Fy equal to 250 and try to rearrange this equation such that I can manage this expression or make it similar to this expression. So the first obvious step would be to send this D on the right hand side. So I'll send this D on the right hand side. 0.531 will be the left hand side, and rest everyone is on the right hand side, including this D which we have shifted to the right hand side. Now shift everybody such that the right hand side becomes this form. Okay, AST by BD. So we'll send this entire portion to the numerator and this entire portion to the denominator to the left hand side. So ultimately what we get is a relation which is similar to what this expression is, but what is missing? The 100 is missing. Okay, so what we'll do, we'll multiply 100 on both sides, doesn't matter. Okay, so if I multiply 100 on both sides, this is exactly similar to what we have as PT percentage. Okay, right, so this is similar to what we have here as PT percentage. Now if I can do this calculation, I will get what is the limiting value of PT percentage for Fe250 steel. Okay, so let's do this calculation. We have, okay, we'll have to get the fraction. So it is 0.531 times 0.36 divided by 0.87 times 250, and this everything is multiplied with 100. This gives us the answer that it is 0.088. Again I am taking 3 significant digits, so this gives me, and this FCK remains as it is, so this FCK you see here. Okay, so this numerical calculation comes out to be 0.088. Okay, so in each design constant we are taking 3 significant digits, so 0.088. Okay, so the limiting percentage for Fe250 comes out to be 0.088 into FCK. Now I have 4 grades of steel. namely I have FE250, I have FE415, I have FE500, and I have FE550 also. So I'll have to repeat all these calculations to get all the design constants for each grade of steel. So instead of doing these repetitive calculations, we can use Excel. Okay, so we'll make a design constant table, which is really important in future analysis and design of beams. So let's start with grade of steel as Fe250. So if you recall, we got XU limiting to be 0.531D. We have MU limiting as 0.149 FCK BD square, and we have PT limiting is equal to 0.088 FCK. Okay, so this calculation, detailed calculations we know. Now we just have to repeat it for all other grades of steel. So I can simply change this 415 steel. We have the XL limiting as 0.479 times D. We have MU limiting to be 0.138 FCK BD square, and we have PT limiting is equal to 0.048 FCK. Okay, now if I go to 500 grade of steel, okay, so now I can get for Fe500, this limiting value is 0.456 times of D. Okay, then we have 0.133 FCK BD square as our MU limiting, and the PT limiting comes out to be 0.038 FCK. Okay, and we have one more grade, that is Fe550, okay, very high strength. So we have Fe550. For that we have the XU limiting as 0.443 D. We have MU limiting as 0.130 FCK BD square, and we have PT limiting equal to 0.033 FCK. Okay, so this completes our design constants table, and these values we have to refer time and again for analysis and design of flexural member like beams and slabs and even footing. So at this point we could numerically get all these values, and subsequent sessions we'll see how these design constants can be used for a section analysis and section design. So see you in next session. Thank you.